Right. Okay. So my name's Ruben. A couple of months ago, I gave a talk on Linux drivers, how we can develop them on the Raspberry Pi, and that was just sort of an introductory talk. So this is kind of like part two of it. So a little bit of background here is that I'm teaching myself how to write drivers basically, and I'm doing it using the Raspberry Pi. So it's quite a convenient tool to use. And as I'm sort of going along, I'm developing teaching slides for it at the same time. And then from my experience, I hope to be able to sort of show other people as well how to do it. I used to work as a field application engineer a lot in the field over the last 15 years, doing a mixture of analog, digital, and sort of software debugging for various companies. And most often I hit the same old problems. This was to do in data communications over Ethernet and Wi-Fi, doing some various contract jobs for various US companies. And quite often I hit this problem that there was something wrong in the driver. So I debug everything on the circuit board, make sure that was all working. And then usually the last problems were then actually in the driver software itself. And I got around to sort of doing some sort of first level debug on these drivers, or figuring out what they were doing wrong, but then I actually wanted to fix the code as well. And at the time I couldn't do that. I had to send the code back to the factory and get a patch. And from that I got interested in how to actually write these drivers. And I've actually got some time to start teaching myself. So it's actually been very hard to find literature on how to write drivers. A lot of it is about 10 years old. It seems like a lot of authors gave up writing around about 2008 or 2009, which is when Linux version 2.6 came on the scene, or just before that. Since then, there hasn't been that much really. So there's quite a lot of scraping around you have to do to try and actually get something that is readable. Quite a lot of the literature is also very academic. You open it, you start reading it, and you don't really know where you are. So my approach is to sort of come from a sort of more engineering approach, or if a hardware engineer wants to learn how to write drivers, basically. So today we're going to sort of focus on how you actually transfer data from an application that's running in, say, user space into a driver that's in the kernel. Right. All the time, I'm using actually a very sort of simple setup. A Raspberry Pi 3, a breadboard, and LED. You'd be surprised how much you can learn about writing drivers. It's just that simple setup, actually. You're writing a driver to control these GPIO pins to turn this little thing on and off. There's actually a lot of code involved, but we'll get to that. So last week we covered, last time, which was end of May, we covered this portion of the driver here, which is the initialization routines and the exit routines. So whenever you load a driver into the kernel, a lot of initialization gets done, which means that memory resources are requested and any other resources that the driver needs. When the driver gets unloaded, an exit routine, at that point you need to very cleanly release all those resources that you used up before. And if you're controlling any external equipment, you want to make sure that stays in a safe state. So this is something that we covered last time, and we also covered how you sort of load a driver or load code, you compile it, and then run it. So I won't go into that again this time, but if you want to see those slides, they're on my GitLab site, and there'll be a reference to that at the end of this. The second major function of a driver is basically to transfer data. So in other words, transfer data from the user application to the hardware that you're controlling, or vice versa, receive data from the hardware and bring it back into the user application. So we'll talk about that today in a sort of rather graphical way, really. I'll show you some code towards the end. The other big part of a driver really is dealing with interrupt requests. This is probably the most important part of a driver. That we can probably cover in another talk some other time. We won't cover that today. That's a big talk all by itself, is how you deal with interrupt requests. And one question you might want to ask is, what you might ask yourself is, why bother writing drivers in the first place when there's quite a lot of difficult coding involved. The reason is drivers work in real time. So any application that requires some sort of real-time response. So in other words, you've got a signal coming in from a sensor, there's some sort of alarm condition that needs to be dealt with straight away at a time that you know when it will happen as well. Then you would write a driver for that, which will run in kernel mode. And as soon as you can set an alarm condition as an interrupt request, for example, and then the interrupt request will generate some sort of service routine and deal with that alarm. If you wanted to send these interrupts up into user land where your application normally runs, you don't quite know when that interrupt is going to be handled or serviced. Any sort of process that's running up in sort of normal user space, the timing of that is always under the control of the kernel. And if there's any higher priority process happening at the same time, your own process can wait there, and you don't know when it's actually going to run. But with drivers, you can control exactly when, or pretty much exactly when they will run and what they will do. So anything that sort of needs, microsecond real-time servicing, it's better to do that in a driver. Right, the types of drivers. So, as you know, Linux comes from Unix, which has been around since maybe early 70s, late 60s. Back in those days, networking only sort of started, or was beginning to start, so there wasn't really much talk of networking drivers in those days. So the earliest sort of forms of drivers were so-called drivers for character devices. So this type of equipment you're controlling here is there you're reading or writing single bytes or a stream of bytes, for example, from a parallel printer port, some of the old serial mice, everything that's sort of pre-USB really. Serial communications. Now, these character device drivers, it turns out they're very handy for controlling GPIO. So that's the GPIO pins, for example, on the Raspberry Pi. The other type of driver are these block devices. So that would be hard disks, USB flash drives. So those were the most common types of devices really back in the early days. And later on came all the others, all the networking ones, PCI Express, USB, and so on. Now, when you're first learning about drivers, you come across these two types here, and they're actually these character device drivers here. They're actually the simplest ones to learn first, really. Then you get onto block devices, and then you get onto the others. So, in division, we sort of split up, if you like, the 3 layers of a computer system or any sort of Linux system, really. It's an area called userland, where the user applications run. And there's the kernel, which probably about 80% of it is actually drivers. You've got your hardware down here. So you've got a driver, which is controlling some hardware. How does the user application interface to this driver here in Linux? Well, Linux provides what's called a virtual file system. And this is a very neat layer. What it does, it makes the drivers basically look like files so that you can read and write to them. The way that we read and write to these drivers is that the application will read, for example, if it wants to read the temperature sensor here through a driver, it will read from a file that you've created in user space. This is a file that you create. For example, we could call it temp sensor. And we create it in a directory called /dev. If you look on your Raspberry Pi, you'll see a /dev directory which contains these device files. Let's say we now want to write to these LEDs. Maybe the temperature's too high, and we want to switch the red LED on. So I'll use the application. So this can be an application that's written in Python, anything, it doesn't really matter, C, Java. And again, we can create device files here. Create a device file for the green LED, create a device file for the red LED. And then we can just read and write these files, and then the temperature sensor can be read and the LEDs switched on and off. Now, how does Linux connect these device files to these drivers? That's something we have to be aware of if we're going to write drivers. Is how these files here in userland get connected somehow to these drivers down here that we've written. Right, so every driver gets assigned what's called a major number. For example, this one is 242, this one here is 243. This is something that the Linux kernel does. It'll assign you a number. And in fact, when you first load your driver, this is one of the resources that you request from the kernel, is to have what's called a major number. And, the thing to remember is with Linux, it liked everything to be in numbers. Anything which has a name is really for our benefit, for humans. As far as the computer is concerned, or the processor is concerned, everything gets a number to identify it. So all the drivers in the system, they will all have numbers. Now, if the driver itself is only connected to sort of one device, then it has what's called a minor number. In this case, we've got a minor number of 0 to recognize this device here. This driver is connected to two separate devices, or two LEDs, and then we can give maybe the green LED a minor number of 0, and the red LED a minor number of 1. And for example, this device file here called green LED, we can link that to this major number 243, so it's connected to this device driver here, and then in turn link that to 0 for this LED here. So this file here will be linked to 243 and then the minor number of 0. And this red LED will be again linked to the same driver, 243. And I'll come into this, how we then link this file to this minor number 1 here for the red LED. So that's what we'll cover next, is actually how these files connected to these numbers somehow. So these devices here are controllable. This is all done with the help of this virtual file system, basically. Now, this is on the slide. For example, with networking, again, the virtual file system will make a network device also appear somewhat like a file as well. So we can use that same sort of idea of reading and writing to devices. mentioned, that was the major number, and these are called the minor numbers here. So they become important in a minute when we come linking these device files to these drivers. If you go to your directory, which will be in a Linux system called /proc, contains a load of stuff. It's become a sort of dumping ground where we use all sorts of useful things. There's a file in there called devices. If you type cat proc /devices, so if you print this file out, first thing you'll see is you'll see a list of all these character devices, so-called character drivers. So these are the name of the drivers here. So these driver names, for example, here's a driver called Broadcom 2835 GPIO memory. It's involved in controlling GPIO pins. All these names, they are actually defined by the code in the driver itself. So I wrote a driver which is actually called LED control.c, or the code is called LED control.c, but the actual driver name that I wanted is called LED control-dev here. That's my LED driver here. And then when I loaded that into the kernel using the insmod command, you might have used that before when you're experimenting with loading drivers. The kernel gave me a major number for that driver of 243 here. So this is the number that the kernel gave me, 243. These are all character devices. For example, these TTY consoles here are character devices. That's a virtual console. That's a character device. The I2C driver you were dealing with, that's it's also got a character device driver controlling it. It's all the information is coming in a sort of byte stream, basically. The SPI bus here has got a character device driver. In this case, on the Raspberry Pi, the driver's got number 153, major number. And again, the SPI bus is basically a byte stream orientated bus, so it would have a character device driver. The other thing you see in this file devices are block devices. So these will be like the SD card, so that SDIO card you slot in actually has they call it a multimedia card in Raspberry or in Raspbian, and it has what's called an MMC driver controlling it, and that has a major number 179. So, and now
I think that's because the same in other Linux platforms that is a multimedia card.
Oh, okay.
So that same driver is used in other Linux platforms. But
okay.
Just has to be the root disk in there.
Oh, I didn't. Okay, I wonder where that came from. Oh, okay. Yeah.
So do these numbers change every time you load the driver? Or is it?
No, you'll see this number here is constant. There's a manual way of getting these numbers, and there's an automatic way. We'll come to that. We'll go through the manual way first, and but what I found with the Raspberry Pi, whenever you load a driver, like the driver that I created here for the LED, switching LED on and off, basically, it always seems to give you the same number, 243. So quite. I think what there are some numbers which are reserved for certain devices. It seems to be traditional. So, for example, TTY here, this device, number 4, that seems to go back to the beginning of time, from the early 70s. So there's a bunch of reserved numbers that the kernel comes up with, and then there's a whole range. Then there's a range of numbers which seem to be free. And so whatever number seems to be available, it gives to you. And this 179 over seems to be 179 whenever you. I don't know if that's a reserve number or not. But the first 10 numbers or something like that, they all seem to be reserved for So yeah. So these are the driver names. They're not the device names, but they're the driver names that are in your kernel. Remember, a driver can control more than one device. Okay, so once we've got this number, we can use that to create a device file, basically, with which to talk to the hardware. So how do we link that major number that we've got from that previous device file? Be careful. So that file that we saw. So we've printed out this file here. So the problem is that lots of files have got the name device in them or devices, so it gets a little bit confusing sometimes. So we printed out this file here, proc/devices, that lists all our major numbers. So this identifies our drivers. So the question is how we link that to the device file that we have in userland that enables us to talk to the hardware. So we run a command here called make nod, and you need to be super user for that. And this is going to make us what's called a device node. So device files also are called device nodes. So we type make node /dev/led. So this is a name that you can make up, LED. I've decided to call my device file in userland just LED. You can call it what you want. You can call it Ruben LED or Richard LED. It doesn't matter. You need to tell Linux what type of device file it is. It's a character or block interface. For GPI opened, it's going to be a character. Then you need to list the major number, which is the number of your driver you got before. This is 243 in my case. And you also need to list the minor number. So the actual minor number that we saw before is going to be related to this file. Well, in my case, I've only got one LED, so I'm only going to be controlling one thing, so it's a minor number of 0. So that's going to create a file called LED in the system directory /dev. We can actually, Linux allows, I mean, if I wanted to, I could create loads of files all linked to this driver. And I could give them different permissions. So you might, if you've got quite a complex piece of hardware, controlling quite a lot of different stuff, but you only wanted some of the devices that it's controlling available to certain people, you could create one device file with permissions for that, and then another device file with permissions for the other devices. Right, now if you look in the /dev directory, you'll when you list all the files in there, if you run ls-l and /dev, you'll see a whole bunch of files there. So all the ones that are beginning with C here, those are character devices. So they're device files which are linked to character devices or character device drivers. Anything with beginning with a B here, that's a device file which is linked to some sort of block driver. In my case, I created this LED device file here. There it is. And the character device, we've got the C there. And you can also see the major number which has been assigned to it. Which, so this comes from that make nod command, basically. Down here, out of interest, here's that 179 driver. And you can see there's 8 instances of it here. So 8 different device files here. The reason being is they've each got a separate minor number here, 0 to 7. So those are basically your eight partitions, 8 disk partitions on the MMC card. So we've got one device file here called MMC block 0. That writes the first partition. That one writes the next one, and so on. So these are all separate device files. But they're all controlled by one driver. 179. So once you've got a device file, you can read and write to it, basically like you can with an ordinary file. So if I wanted to see what the status was of my LED, I can just type cat/dev/LED. If it was on, I get the number 1 back. Likewise, if I wanted, but if I wanted to write to it to turn it on or off, I could do an echo command, echo 0 or 1 into this file here, and it will turn the LED on or off. Now, this command make nod, it's okay for sort of manually naming your GPIO device files. I've got to do this for hundreds of devices and run this make nod command every time. Every time you loaded a driver and you had to link it to a device file somehow using make nod, that will get a bit laborious. So for hot plugging and sort of automatic device naming, Linux uses a device manager called udev. But for experimenting, this is fine here. Right. So now we want to actually move. We've linked up the device files in user space to the driver that's in the kernel. Now, how do we actually sort of move data between them? So, a little bit of background. On the Raspberry Pi 3 board, for example, you've got 1 GB of RAM. That's sort of the physical memory that's available. If you're running Raspberry in sort of 32-bit mode, you can do 32-bit addressing. In theory, you can address sort of 4 GB of address space, basically. But we haven't got 4 GB on the board. We've only got 1 GB actual memory there. So in the RPi, there's a memory management unit, and what it then does, it takes anything that's stored in RAM. It can swap that into a virtual address space of 4 GB, which will be on your SD card, basically. So it'll use your SD card as swap space. So any application that is running, it can be storing data on your SD card, and as that data is needed, it gets swapped into RAM here by the memory management unit or paged in. Now, that brings up some challenges. The fact that any data that the driver needs, or it needs some sort of memory location that the application is requesting data from a driver, or the application wants to send data to a driver. That data might not yet be in RAM. It might still be on the SD card somewhere. And at the same time, the drivers that are in here are trying to pull data in from user space and send data into user space. They don't know yet if what's being addressed is actually in RAM in main memory, or on the main RAM, in that gigabyte of RAM, physical memory. Okay. These drivers that are in kernel space, they're basically in RAM itself on the board. That's where they're running. But any sort of application data, we don't actually know where that is. If we're from a driver point of view, we don't really know where this is. It could be in RAM on the board, or it could be still waiting to be swapped in, still residing actually on the SD card itself. So we can't do a sort of straightforward read and write between kernel space and user space. Any pointers in this code that's pointing to a memory address location here could be pointed nowhere, because that data might still be on the SD card and not in the RAM itself. So we have to invoke special functions that can copy data reliably and securely from this space to this space, basically, and vice versa from here back to there. So in the driver code, we have a special function called copy from user. And what we need to do, we need to set up a buffer in the kernel space, so in our kernel driver. We're going to, I'll show you in a minute, we'll set up a buffer also in the application code. And then what this function does here, copy from user, as soon as that's invoked, it actually waits until the buffer, the right buffer, becomes available in RAM for the user application to send data through this device LED file here that we've already set up previously. And then we can suck the data from there, put it into the driver, and turn the LED on. This is a very neat function. It basically sleeps there until this buffer becomes available in RAM with data from the application. And likewise, when we want to send data from the driver to an application in user space, it's got something to send, copy to user here in this case. Again, it will wait until a buffer here becomes available, and then we can send the status of this LED into the buffer that's available in RAM, and then the application can do something with it. Let's look at how we would do a simple web application to control a driver like that. In this case, use some Python here. So we've got a Python file called controller.py. This will display a web page with a couple of buttons on it for turning the LED on and off, and also for showing you what the status of the LED is. The actual code that talks to the device file that we've created here, it's going to be done by LED control.py. And then we can use this interface file that we made with MakeNode, send data through the virtual file system, and then to the driver that we wrote here. But we'll have a quick look at this code and then a quick look at this code, but we won't spend too long on this because it's a huge piece of code. But just to give you an idea what the difference in code sizes is. So the code for the web page, that's pretty much it. Not a lot there. We use a thing called a Flask web framework. There's some Python utilities that are available for creating a very simple web page, basically. Got this code here for the LED turn on and off buttons. A little bit of code here to read the LED status. So all this does is set up a web page with a couple of LED on and off buttons, and also a little display for displaying LED status. Then the actual bit of code, this is in a separate file called LED control.py, which sets up that buffer that we were talking about in user space, where we can send a 1 or a 0 to, which then gets sucked into the driver to turn the LED on and off. That's what this code basically does. So here we reference this file, the interface file /dev/LED that we created before. Then here we do a read from. So we here's the buffer. We set up the read buffer. Here we can set up the write buffer. So there's those two. So we've got separate read and a separate write buffer basically. Again, that's all the code there is on the Python side of userland.
Just out of interest, what's O_RDWR? So the second parameter on open.
This is the file mode redirect.
Oh, rewrite.
Which that you said? RDWR. Rewrite.
Rewrite.
Because you can specify the query could be a read only.
Oh, okay, I see.
So we can either write a 1, turn the LED on, or write a 0, turn the LED off. So that's the page. That's what it looks like. Not much to it. So one button for turning on the LED, one button for turning it off, and then whatever the status is up. That's a fairly simple piece of code for that lot. Now, if we were to just have a look at the code for that's not displaying. It's a bit of a okay. Can't really see very much. But this is the C code. All I wanted to do was just show you the size. The previous Python code samples we saw were very short. But in comparison, you'll see that this is just a driver for turning LED on and off, basically. So it's doing something very simple. But you'll see actually there's quite a lot of code. You can't really see it, but I'm just going to basically just show you the size of this code. There's probably, you can see there's lots of lines. There's how many lines is here? So we've got.
So is it really hard to debug when you have fucking kernel space? You have to like.
You can.
If it doesn't work, it's essentially screwed.
There are. And you can use what's called a special print kernel function. It's a bit like printf and C. So if you put those in, that can help you. And there are sort of kernel debugger tools as well. For a relatively simple piece of code like this, even though this is a lot of lines, this is not getting on to a couple of hundred lines. This is
Quite a lot of that is boilerplate. It's standard for almost all drivers, presumably.
yeah, I mean, there's always the thing with I mentioned, yeah, there's coming a little bit of ground that we did last time. But so in a kernel driver, you don't have a main function like you do in a normal C program in user land. So the entry point for a driver in kernel mode is you have an init function basically that requests all the resources. And that resource requesting, there's a lot of code for that. So you need to request a certain amount of memory. You need to request these major numbers, minor numbers, and so on. And then you need to set up all these file operations. So this business of copying data from the user to the driver and vice versa, sending it back again. There's quite a lot of complex file operations that you need to set up in the code. Now, a lot of that you can cut and paste from other drivers. It's not too bad. And then you also need to check that there's sort of no overruns in the buffer and things like that. So there's always this sort of buffer management going on as well. And in this driver, for example, you haven't even got any interrupts yet. So although it's doing something relatively simple, we've got what have we run? You can't see it around here, but yeah, we're close on 300 lines here already.
What's your grand plan then after now that you know how to write a driver? You're gonna
Take over the world.
No, well, actually, what I'm working. I've got a small sort of small business startup grant basically to develop training courses for writing drivers. So I'm going to put some. I'm going to hopefully start putting some of this on Udemy once I've got more of this going. And as I said, I'm trying to do it more from a hardware engineer's perspective, not make it too academic, and have quite a lot of graphics explaining what's going on. And the other thing is I need to make a book proposal as well. I'm talking to one publisher at the moment, and so that's kind of the grand plan at the moment with this. And then, actually, in fact, this is also why I was interested in the LoRaWAN stuff. So I'm kind of doing it in topics. So we start off with some very simple GPIO drivers, then we move up to something a bit more complicated. And then the last thing is going to be a network driver example. But I didn't want to do all the old stuff that's previously been done with normal network drivers. So I was going to use LoRaWAN as an example for developing a network driver. So that's where that will be kind of like the last chapter. Well, almost the last. One of the things is happening a lot is in actual systems, you'll very often have the main processor, something like a Raspberry Pi equivalent, acting as a sort of management processor. And then you have an FPGA, which is doing real sort of fast stuff. And you rely on a management processor, like a Raspberry Pi, to download a Linux stream, some sort of byte stream into the FPGA, set all that up, and do some sort of hardware accelerated processing. So part of the book or part of the course will be to explain how you do that as well. So how you use your Raspberry Pi to control an FPGA and download code, write a driver which will download code from your Raspberry Pi into the FPGA and then control that. Kind of modern. So it's to try essentially update what was written 10 years ago to slightly more modern times now. That's the grand plan, but that might take 5 years.
Yeah.
So
that's what a trick out a device that you're trying to write a device driver for.
Sorry?
This wasn't a trick. There's a device that you're trying to write a device driver for eventually.
Yeah. It's to I did a lot of work with when I was sort of doing technical support, basically, I was often, again, it goes back to this problem. We were doing sort of working with my other hardware colleagues and so on. We wanted to learn how to write drivers in a sort of more simple way, basically, in a sort of less academic way, and also have a tool on which you can learn this stuff without having to spend a lot of money. So this is where the Raspberry Pi sort of came in as an idea. Because there are quite, if you, TI, for example, have got some very good learning tools, but you have to buy a TI board and things like that. And you kind of get locked into their way of doing things. ST as well, they've got some good systems. So the idea really with using the Raspberry Pi is kind of making it a little bit independent and have anybody can It doesn't just have to be engineers; it can also be students and so on. Yeah. Use that as a vehicle for learning how to write device drivers. But yeah, that's the plan. I suppose the one problem with it is Broadcom make very little data available. So when you write device drivers, you have to really know what's going on in the hardware. You need access to registers and things like that. With the Raspberry Pi, you end up having to do quite a lot of guesswork to find out where certain registers are, or you have to. They publish virtually no data sheets, real hardware data sheets for those devices, unfortunately.
So presumably you can't, for example, use the GPIO character device inside a device driver. Can you?
Yeah, I often find device drivers actually stacked. Yeah, you can. Yeah, you can. I mean, actually, when you write these GPIO device drivers, one of the things I've had to do was disable the Broadcom one. And there are ways of doing that. Luckily, you can, because of the GPL license, there's quite a lot of code from Broadcom you can actually look at, and then you can see what they're doing.
Actually, the GPIO is quite well. There is a program manual for the specific GPIO that is quite good.
Yeah.
But some of the other bits, the Broadcom chips, particularly the graphics, are not documented.
That's also been released with video for documentation. It was last year, 2 years ago.
Okay.
They are trying to be better at making material available, even though it's not easily digestible by somebody who's not familiar with it in terms.
Some manufacturers regard that as competitive, potentially competitive information, and that's rampant in the graphics industry.
It is their IP, so
yeah. GPIO is also, it's been designed in a very nice way that actually allows different drivers to share, different drivers to access different of the pins without trampling on each other. The actual commands for the GPIO they thought about that very carefully, which is quite nice.
Yeah, that's true. We had to do a bit of a friend's been helping me with this. We had to do a little bit of with the RPi 3. We had to do a bit of guesswork while looking at the drivers to figure out where the GPIO base address was.
Yes, that is an issue.
It's different from the RPi 2. Yeah.
And there isn't a document for the current Pi. That's correct.
Yeah.
And it's not the same base address. You have to wander around and try and find where it is.
Yeah, it's things like that you have to. Yeah.
So the BCM CPU is a slightly higher version of it on the Pi 3.
Yeah.
Because I know they're different. The one in the Pi 0, for example, goes back to the original generation that was used in the original Pis and the 8s. And then in the Pi 2, they actually put out a newer version. So I assume the Pi 3 is again another.
I think it's got a 1-digit increment on the end.
Something along those
lines. There's no document for that. So it's exactly the same as the Pi 2. I need to set the base address.
Okay. If you look at my
layout, the same. But
Sorry, just have one more presentation as well. So.
Sorry.
Is it okay? We're just gonna.
Oh yeah, sorry. Yeah.
Sorry.
Yeah, no worries. If you are interested in the GPIO stuff, if you look at my previous month's, or the end of May month's presentation, you'll see the GPIO base address given in that Pi 3 if you want to use that.
So one more talk, Michael. Thanks very much. Let's use the.
That's my beer.
Oh, sorry.
Hi, so I haven't got any slides. There will be something up on the screen in a sec. what I've been doing is something that I'm bringing to EMF camp. Some of you have told about the idea before, so sorry if you've heard it before. The general idea is, if anybody's played Ingress, the idea is that there's going to be these orbs. So I bought this, realised that looked a bit rubbish. So I sprayed them so that they're frosted, so you can put LEDs in there, and they should glow rather than just light up as an LED. And the idea is that you get an RFID card, and there's 3 teams, and you tap your RFID card, and it will change it to your team's colour, and you'll capture it for your team, and then the longer you hold it, the score builds up for your team. And capturing individual stats like how many of these orbs have you visited, how many of them have you captured, how long have you held one for, what's the longest you've held it for, all sorts of information you can gather from these. The basic idea behind it is, I'll get out the board here, which hopefully survive the underground. So this is a prototype board. At the heart of it for Wi-Fi is an ESP 8. I always get them on 866. Yeah, that's the one. So it's one of them, and that does all the Wi-Fi comms. The problem with these is that they're reasonably high power drain compared to other things. So I've got a PIG chip, and the PIG chip can run in almost no power at all when it goes to sleep. So the idea is that the PIG chip kind of runs stuff, runs the orb. And this is the Wi-Fi, as an RFID reader. And what happens is the PIG chip wakes up once a second, flashes the LED of the team that currently owns this orb, and powers up the RFID reader and sees if a card's being presented. And then if there isn't, it turns itself back off again and goes to sleep for another second. So that way I can run this off a battery for several days without it being a problem. The Wi-Fi module, when it actually has something that happens and is presented a card, it turns this module on, and that module then provides the Wi-Fi connectivity back to the Raspberry Pi, which is on the floor, that's running the actual game. So the basic tech here is I've got PIG Basic is it's a compiler that compiles down to an assembler file that can then be programmed into this. This I've actually programmed with MicroPython because I'm running the main game in Python on here, so I wanted to keep the number of languages down to as few as possible. So this actually has a little facility where it can self-update. So it can download, update MicroPython firmware from the Raspberry Pi as I publish new versions. And what happens is the PIG chip purely talks to it across the 9600 BPS serial link, and it just sends it one letter or however many letter commands it needs. That gets relayed back via MQTT to the Raspberry Pi, where a Python script is running the actual game that's running all the scoring, and it saves it into a database, TinyDB, which is basically it's a very primitive database, and it saves it into a JSON file. So all of that data is stored in there, and it's very easy to retrieve. And I don't know how well it will scale. I'm going to have to find that out in the field, but we'll see how that goes. So the main thing is that it's all MQTT messaging between the two. The way that it finds this particular Raspberry Pi running the game server is when this powers up and it joins the Wi-Fi network, it sends a multicast out on a particular address that says Marco, and this responds Polo, and at that point it knows its IP address. So it then does an MQTT connection to that server, and at that point it can start sending messages to the game server, which the game server then responds back, and this then knows what's going on in the game for it at that particular time. So what I'll do, I neglected to bring the cable that connects my laptop to an HDMI, but I will plug it into my Pi. I'll have to reboot.
I'm thinking of people that will be going to the thing. If this is published before you go, well, they're all going to know that there can be lots of people responding to Marco.
Well, yeah, I mean, it's. I'm not going to publish that kind of detail in advance.
It might be on video now.
This isn't intended to be hyper secure or anything like that. Okay, yeah, there's the low voltage. So we're just waiting for that to this. Oh, there we go. Once this is booted up, we can then connect on and show you. Just have to log in to get this running. One little thing I have done, these LEDs along here show the current team that's owning it. There's a white LED which is neutral, and the red LEDs at the moment don't show up very well because the voltage is a bit funny, so they don't light up very well. I've got to figure that one out first on my to-do list. Right, well, let's fire up the game. I don't know if you can see on there, but it should show when you start getting connections through an MQTT. So there you go, got a connection there. Right, so this is a map of EMF CAN, and at the moment we have 1 all, which is currently green. So that's showing you that that's where it is, and the score at the moment, greens are kind of winning at the moment. It's been like that for a while. But what will happen is I have a bunch of RFID tokens in here. Just power this up. So just take a moment to wake up. So it's a bit funny on the first boot up for some reason. Timing thing. So we should get okay, yeah, that's alive. So you can see, I don't know if you can see, it's flashing green at the moment, show the green's own it. So I have a blue token, which I'm going to present to it. Flashes white to show it's read the token. What's happened now is that green light will flash faster and faster and faster to show that somebody's trying to take this particular orb. The green player could present his token and block that person capturing it. The idea being that way there isn't this constant to and froing, and if you defend it, that person then can't capture it again until somebody else tries to capture it. So there we go. They've successfully captured it. You should see that it's changed to blue, and that's now changed to blue on the map. And the score on blue, which is currently 69, should start increasing. It takes a moment to there we go, 81, and very slowly you'll see that change. You see that blue for 1 blue has visited the orb twice now, and probably has 2 captures as well. So it gives little stats for the individual players. What I've also done is this is a new feature, so let's hope it works. This is a frog that hasn't played the game before, so it's going to present itself to there. It doesn't. So what happened is it doesn't know it, so it's now going to start flashing the white LED in theory. There we go, and then it will start cycling through the different colours, and you can pick which colour you want to be. There's blue. Now it's red. Now it's green. I want to be on the green team, so I present that. And then, in theory, it will start flashing quite rapidly. If it's worked, I said it's a new feature, it may not. But that's the general idea of it. Yeah, that may not work. There you go. It's a new feature. Anyway, that's basically it. Any questions?
What generation of tick are you using? What variant of tick?
It's one of the more recent ones.
16-bit? Because I think MicroPython is supported by the 16-bit ones, or a subset of those.
Okay.
If you have a large enough one to hold the memory requirements.
Yeah, I think that would probably be overkill for what I'm trying to do, because a lot of it is, so I'm using a pick 16F15345. The main reason for picking that particular pick chip is that it's got remappable I/O pins, so I can take any of the built-in features that it has, like serial port, SPI port, and I can map it to almost any pin on the pick.
Okay.
And the idea is that then I can quite easily pass out a straightforward bus to the relevant component I'm trying to talk to, rather than having to kind of run a wire from there and that pin, and that's which is what I had with the previous generations.
I'm wondering, could it be modified to use a microbit? I'm just thinking, sort of thing kids could play with a microbit. It has a similar, obviously I haven't got it.
I mean, sure, you could replace the pick with the microbit, but I don't know what the power utilization is. My main reason for the pick chip is that it can go into very low power mode. So actually the idle power is incredibly low. Yeah, maybe.
How much time do you have left before the camp?
Well, the PCBs are ordered. I would show you a visual if I could get it on the screen, but I don't think there is a VGA connector. The boards are ordered, all the parts are ordered. I'm just crossing everything that they arrive in time that I can assemble them in time. And that the PCB works, because unfortunately I've not had a chance to actually work on it enough in advance to actually get a prototype built to then test it. So I've ordered a bunch of boards and hopefully work.
Well done, get this far. It's really impressive.
But the board is circular and just sits in the bottom, and then the RFID reader board there will just sit underneath it. And the battery, originally I was going to go with these lithium-ion battery packs, but unfortunately the company has suddenly decided they're not stocking them at the moment, so I've had to just buy lithium-ion cells, and going to have to figure that one out. They do fit. How well, I don't know.
How many are you going to deploy?
Depends on how many I manage to build.
What's the best case scenario?
40.
40.
Your PCBs are SMD or through hole
Combination.
depending on what the components.
Yeah, I've gone with SM where there wasn't an alternative, and I've gone with through hole for everything that I could, just because it's
quicker to solder.
Yeah, exactly. It's less fiddly, so I'm more experienced with through hole. So this will be my first bit of SM soldering, unless I can get Nick to do it for me.
Oh, I'm choosing it.
So yeah.
So I've got a quick question. So what's the intent here? Is it that you find a piece of land, you hide these orbs, and you get people to just track them, or?
Well, so EMF Camp is an event that happens every 2 years, and they move the location every year as well. But effectively, think of it as Glastonbury for geeks. So when you go there, it's everything. Everybody just brought stuff they've made. You've got everything from people who've created a giant inflatable bunny that lights up different colours depending on what you tweet it. To the robot barman that you can send a message to and it will dispense a drink for you. You know, you can do blacksmithing, you can do all sorts of stuff there. It's just an eclectic collection of people that likes to create stuff and have brought along their creations. So this is what I've mainly built it for. And the idea is with this, if you see here, you've got sort of the camping up there and there, but a lot of this section here is all the stuff that's going on at the event. And I'll hang the orbs around there, and I'll probably hang some far reaches of the site as well. And then I'll just make sure that they show up on the map in the right places. It's just a game, and it's a bit of fun. And see which colour wins. Oh, it does show you when there's a capture occur there, just then on the scroll of what's going on, as well as the ticket of the individual scores.
Any other questions? Cool. It's a fun project, thank you very much. Cool. Cool, that's it. Over the pub. We don't have a meeting in August, but there's another one in September. So if anyone's got something they want to present, do drop me a line. Don't forget the Facebook group and meet up, all that sort of stuff. Cool. Thank you.
Thank you.
Thanks for organising. Cheers.